and switch on your camera. Professor Penching Liu. Professor, I think you already joined. I gave the permission to you. Hello, Professor.
Hello, everyone. Can you hear me?
Yeah, you are audible. Please increase your volume, Professor. Please.
Okay. Okay. Let me see how I
Please.
can share my screen.
Yeah, you are
So
audible. You are audible. Excellent. You are audible now.
okay. So I can start now, right?
Yeah. 1 minute, Professor. I'm going to introduce about you.
Okay. Yeah.
Yeah.
Sure.
Thank you. Actually, today the second session, Professor Penching Liu. Actually, he's a eminent professor in University of Arc. Actually, I'm going to, it's my privilege to read the biodata of Professor Penching Lee. He's an associate professor in robotics and applied control, chair of the graduate school board, and director of the computational autonomous learning systems lab at the University of Arc, UK. Previously, he held academic positions at Cardiff Metropolitan University, the University of Lincoln, and Jincheong University of Technology. He earned his PhD from Bournemouth University in 2017. And Professor Liu is a key member of initiatives such as the RTDS Group, AR Robots, ISA, and AIP, focusing on the safety and autonomy of robotics and AI systems. His research interests include bio-inspired robots, robot learning, applied control, and intelligent systems with over 100 publications and involvement in research project with 3.5 million pounds. A fellow of HEA and an active member of IEEE and related committees, Professor Liu serves on several editorial boards and international conference committees. He has received numerous accolades, including the IEEE Outstanding Associate Editor Award in 2020 and Web of Science Global Peer Review Awards in 2019. Additionally, he contributes to grant review panels fostering research excellence globally. Thank you, Professor, accepting our request. Now, session is hand over to you. You can continue, Professor. Yeah, please share your presentation, Professor.
Okay. Thanks, Dr. Ravi.
Yeah, please
Uh,
share.
okay. Let me share my screen. Okay. So can everyone see my screen now?
Yes. Your
Okay.
screen is visible, Professor. Make it in
Yeah.
full screen. Make it in full screen mode, Professor.
Yeah.
Yes.
Yeah.
Yeah.
It is
Yes.
okay now.
Yeah. Now it is okay, Professor.
Okay, great. Okay, thanks, Dr. Davi, for the invitation, and good evening, everyone. So it's an absolute honor to be here today at the faculty development program on importance of AI in robotics. So as Dr. Davi introduced, my name is Penching Liu, and I'm an associate professor in robotics and applied control at the University of York in the UK, United Kingdom. So today I'm honored to present on the motion planning algorithms from theory to application. So in this talk, we will explore the transformative advancement in motion planning, moving from theoretical foundations to real-world implementations that are shaping the industries. So to get you through this session, so here are the outlines. So we will begin with introduction to York and our research interests and visions, and then we will dive into motion and path planning, as well as long-term motion learning architecture, which is a recent work developed by my team. And finally, we will look at some future directions in this area as well, followed by a call for collaborations through PhD applications, academic visit, or staff-student exchange, and some call for papers from the special issues I'm currently organizing, and also the conference that I'm organizing this year. So let me start by introducing where I'm come from, the historic city of York. So York is a city steeped in history, located in the north of England. As you can see from the map, that is very close to Leeds, Manchester, and Liverpool, and not far away from London. It's over 2,000 years old, dating back from the Roman times. And what makes York so special is how its ancient charm merges seamlessly with the cutting-edge research and innovations, making it an ideal home for work in robotics and AI. And as the former capital of England, so York is renowned for landmarks like York Minster, which is the biggest church in Europe, and the shambles and these Roman walls that have stood the test of time, and also the historical setting inspires our pursuit of innovation. So we will look to the future while standing firmly on the foundation of the past. So now let's talk about the institution where all this work takes place, which is the University of York. So the University of York is a member of the prestigious Russell Group, known for the research-intensive universities in the UK. So globally, we are ranked 147 by the THE and 184 by the QS ranking. So nationally, we are recognized for research quality and hold a Teaching Excellence Framework Gold Award for teaching excellence. So at York, our work in robotics and AI is setting benchmarks, so driven by state-of-the-art facilities and focus on impactful research. So overall, the research ranking, so we ranked at 10th in the UK for quality of research. And the Department of Computer Science at York has been a pioneer since its inception in 1972, with a RAF ranking, which is a Research Excellence Framework. We placed in equally ninth in the UK, as you can see from the slide. So we're behind Imperial College, Oxford, Birmingham, UCL, Edinburgh, and etc. So we are ranked the computer science subject. We are ranked in number 9 in UK, and we also have over 140 postgraduate research students, which including PhDs and master-based research, and a thriving undergraduate program, which is about 800 undergraduate students in the department. So this collaborative environment fuels our innovative research in robotics AI. So here's where the Department of Computer Science reside. So the in one building, so which is a modern purpose-built facility that hosts the Department of Computer Science at University of York. So it's part of the university's continued investment in cutting-edge infrastructures to support education and research. Also, the building is named after Ian Wand, a pioneering figure in computer science, and honoring his contribution to the field and to the department. And here's the video describing the department. So the building itself is shaped in the capital letter C, as you can see from the video, which represents the word computer. Half of the building is used for staff offices and the research labs and meeting rooms, and the other half is used for software and hardware labs for teaching and research. So as part of the larger computer science hub on the campus, so the in one building represents a commitment to foster innovation, collaboration, and academic excellence. So this slide shows some inner space of the department. As you can see that how we teach the subject within the lab and within the classroom, we're using the flipped classroom technique. So a lot of interactions with the students during the class, and a lot of very good facilities to initiate conversations with students. And also, York is home to the 9 world-leading research groups within the department. So each tackling critical challenges in various domains, including AI, automated software engineering, cybersecurity, human-computer interaction, and vision, graphics, learning, and real-time and distributed systems. So today, I'm a keen member of the real-time and distributed system group, so which leads the change in advanced robotic and autonomous systems. So let's take a closer look of what we do. So our research group, established in 1990, so focuses on system where timeliness, coordination, and distributed computing are crucial. So here are the academics and postdocs, and also the PhD students are listed on these slides. So from robotics to healthcare and high performance computing, so we're aiming to address challenges that demand precision and adaptability in real time. So this interdisciplinary approach is key to ensuring that the robotics and autonomous systems are both functional and reliable. So the application areas include embedded computing, Internet of Things, telecommunication, robotics and autonomous systems, automobile, industrial process control, healthcare, and high performance computing. As I mentioned, so we are committed to pioneering robotics and AI research. It's driven by its world-class research centers. So each of those centers focus on addressing critical challenges while pushing the boundaries in this area. So for example, Assuring Autonomy International Program, so which is dedicated to ensure the safety and reliability of the robot and autonomous systems, and also the UK RIAI Center for Doctoral Training, so which is the first doctor training center in the UK, specifically looking at lifelong safety and assurance of AI-enabled autonomous systems. And the Institute for Safe Autonomy, I will come back to later in a few minutes. And so those centers are where cutting-edge ideas meet practical applications, so which makes York a global leader in robotics and AI research. So the Your Robot Research Center unites researchers from diverse disciplines with a shared interest in robotics and autonomous systems. So this collaboration fosters innovation across areas, for example, like medical robotics, swarm intelligence, and ethical AI. And by leveraging this interdisciplinary approach, so we're addressing both the technical and the societal aspects of the robotics and autonomous systems issues. So at the University of York, robotics and AI research spans a remarkable breadth, engaging experts from at least 11 diverse disciplines from the 11 departments. So this cross-departmental collaboration enhances our ability to tackle more complex challenges from multiple perspectives. For example, from chemistry, computer science, electronics, and also mathematics, psychology, etc. So our research focuses on designing systems that are advanced, which means we are going to employ the state-of-art methodologies to push the technological boundaries, and also they should be ethical and trusted. So which means we're developing AI and robotic systems that are socially responsible and gains trust from the users. And also those systems should be safe and reliable. We ensure the systems operate effectively, even in some unpredictable scenarios. So those are the principles which are guide our efforts to create mobile and autonomous robots that are not only intelligent, but also dependable and ready for real-world deployment. So next, I will explore some of the application areas we're working on. So the research has far-reaching applications, which aims to address critical needs across industries and environment. So some of the key areas include the harsh environment, for example. So which means robots are designed to operate in extreme conditions, for example, such as space exploration, some underwater missions, and also to do some kind of a decommissioning works in the fusion reactors and repair and maintenance works. And the other applications, autonomous vehicles, for example, so pairing work in navigation and control for for example, the drones and self-driving cars. And the other areas, medical robotics, innovating in surgical assistance, rehabilitation, and diagnostic tools. And also the swarm robotics, developing collaborative systems where multiple robots can collaborate seamlessly. And also we're doing some some applications in agriculture and aquaculture to use robots to optimize the tasks like crop monitoring, pest control, and sustainable farming. So those are the application areas, underscores our commitment to solve the real world problems through technological innovations. And so our work is at the forefront of the robotics and AI research, and which spans several application domains, as mentioned, from developing robots for harsh environments like space and underwater to advancing autonomous vehicles and medical robotics. So here are some of the examples, the robotics and AI projects that are funded at York and computer science. For example, the TQ-bot, so which is we're developing a next generation bionic quadruped robots designed to excel in dynamic and complex environments. And also for example, the other one is bio-inspired dynamic vision systems. We're aiming to leverage the biological principles to improve the visual perceptions in robots. And the other one, for example, Nanoman, we're developing nanoscale manufacturing platforms for multi-scale precision. And the other one is trajectory learning for robotic arms. For example, we're focusing on autonomous learning in some context-rich environments in order to improve the performance for some of the manipulation tasks. So each of those projects reflects how we create ethical, safe, advanced, and reliable systems, and how we are going to meet the real world needs and tackle those challenges through the innovation. And so here are some examples where of our work in intelligent systems and robotics, including some groundbreaking innovations. For example, the modular robots, which are capable of self-recognition to adapt to various tasks, and the tensor-grid robots, which are flexible and adaptable systems designed for robustness and efficiency, and the medical and evolutionary robotics, which are focused on adaptability and learning from the biological systems to improve the design and functionality, and also some the multi-sensor fusion, which are enhancing the situational awareness through advanced data integration. And the other aspect is manipulation of deformable soft objects, so which are enabling robots to be able to handle delicate or deformable objects more safely. So the next is our research also addresses some of the most pressing challenges in robotics and AI today. So for example, the resilience systems in swarm robotics to ensure coordinated behavior among robotic swarm in unpredictable environments, and human adaptive learning to develop robots that can learn from human interactions and adapt in real time. So I will come back to this area later in the later slides. So the other aspect is to timing of optimization in manufacturing. So improve the efficiency in smart factories by ensuring tasks that are completed on time and the resources are utilized more efficiently. And the other is the timeliness in wireless networks. So we're designing reliable and time-sensitive communication system for autonomous applications. So each of those areas have far-reaching implications from manufacturing and healthcare to transportation and beyond. And we also place a vital a pivotal role in UKRI Trustworthy Autonomous System Program, which is a 33 million pound initiative aimed at creating autonomous systems that are both trustworthy in principle and trusted in practice. So we have a huge contribution towards the verifiability node, which are led by the robot staff, focusing on ensuring the autonomous systems meet rigorous verification standard. And also we're contributing to the resilience node as well to tackle the challenges of building systems that can recover from failure and adapt to dynamic and complex conditions. So these programs aligns perfectly with our vision of developing socially beneficial technologies that instill confidence in users, industries, and governments alike. At the University of York, the Institute for Safe Autonomy, or ESA, as I mentioned earlier, is a flagship initiative addressing the global challenges in ensuring safety for autonomous systems and robots. So we have more than 35 million pounds invested. So ESA is a hub of interdisciplinary collaboration, combining expertise across academia, industry, government, and civil society. So its mission is simple but critical: to design, develop, and rigorously test robots and autonomous systems to ensure their safety, and also is setting new standards for the development and deployment of robotics and AI as well. So I'm a key member of the ESA. So at ESA, over 100 researchers work together to shape the future of robotics and autonomy, from safe software to reliable communication systems. So the ESA's work is organized into 4 fundamental research pillars, of which the first one is design verification, so developing rigorous frameworks to test and validate the safety of both software and hardware for autonomous systems. And also the second one is assurance, to tackle the challenges of regulatory compliance and public trust to make autonomous system more acceptable and desirable, and also communications to innovate resilient communication mechanism, including quantum communication technology, which is vital for secure and reliable operations. And the last one is society and ethics, to apply practical ethics to ensure those technology aligns with society needs and values. And so we have the most advanced facilities in the north of England, so which is represent a state-of-art living lab for research, testing, deployment, development of autonomous systems. So, for example, we have a 6-meter high indoor test space for evaluating ground vehicle and water drones and also aerial autonomous systems such as drones. And we have 18,000 liter underwater research tank to simulate and test the aquatic underwater robots. And we also have some anti-vibration quantum optical tables, which enables high precision experiment in communication technologies. We also have a rooftop lab and telescope to test the system in outdoor environment. So now we have explored the broader research environment at York and the department, and some of the facilities of the we have. And now I'm going to shift the focus to my personal research interest and my research visions. So this session will highlight the core theme driving our work in a computational autonomous learning system lab and of a research vision for the future of robotics and AI. So as Dr. Ravi introduced, so my academic journey has been shaped by a multidisciplinary background in control systems, mechatronics, computer science, and electronics engineering. So as an associate professor and a member of York's real-time and distributed system group, and also member of Your Robots and member of ESA. So I've secured over 3.5 million pounds in grants from the funding agencies and organizations such as EPSRC, Innovate UK, and the British Council. And I've also contributed to over 100 publications and served as editor for some leading journals in robotics and AI, such as ICRA, which is top tier conference, and also robot learning and PhD computer science. And my lab, the CARS lab, the Computational Autonomous Learning System lab, fosters collaborations among lecturers, postdocs, researchers, PhDs, and undergraduate interns. So working together to push the boundary of lifelong learning and autonomous systems. So next, I'm going to introduce briefly my lab. So the CARS lab brings together a dynamic team of researchers to address the cutting-edge challenges in robotics and AI. So our team includes 2 postdoctoral researchers like Dr. Yan Wen and Dr. Ishrak, and also the PhD candidates such as Xiaoliang Zhang, Shi Baoyang, and Claire Hinton, and some undergraduate researchers exploring some exciting projects with me. And we've also proudly seen several of our graduates, such as Dr. Jiaji Yang and Dr. Shuyang Hu, go on to academic and in industry leadership roles as well. So our mission is to develop a system that can learn and adapt throughout their lifetime. So which I will discuss further in the next few slides. So I've now explained examine the inspirations behind our research. So biological systems, as you know, that such as animals, insects, and even human beings are capable of adapting to their environment throughout their lifetime. So they learn from experience and improve their behaviors and performance dynamically. So this ability to learn, adapt, and evolve continuously is what we aim to replicate in the machines such as robots. So imagine a robot capable of acquiring new skills without compromising its prior knowledge and adapting to new environment and optimizing its performance. So all while conserving resources like energy and memory. So this is what we call lifelong learning. So the new generation of robotics AI applications would require a fundamentally new type of machine intelligence. So those systems must acquire new skills without forgetting the old ones, and adapt to changes in the surrounding environment, and also apply previously learned knowledge to the new tasks. So all of this would need to happen while balancing the constraints, such as limited computational power and limited energy efficiency, limited memory resources. And developing such lifelong learning machines is at the heart of our research, and it drives its applications across the domain. So our vision lies in bridging the gap between biology and robotics to create those intelligent systems with lifelong learning capabilities. So by understanding the adaptability and autonomy found in the biological systems, we aim to develop the robots that are resilient and energy efficient, and flexible and adaptive in their interactions with humans and their surrounding environments. So this research vision has applications in areas such as human-robot collaboration, which I will talk about later in the slides, and soft robotics, agriculture and aquaculture, environment monitoring and environment control, and embodied artificial intelligence. So those innovations are shaping the next generation of the robotics AI systems. So to generally summarize our research vision, so we aim to develop intelligent machines that behave like the biological agent. So those machines will never stop learning, continuously improve their performance with their experience and interaction with the environment, and also operate with minimal resources demand. So our goal is to create systems that adapt dynamically to some new environment and challenges, enhance their utilities across industries. So lifelong learning is not just a concept, it's a foundation for the next wave of robotics innovation. So here are some of the project of collaboration and partnerships we had. So we formed partnerships with leading institutions across the world, and based on the funded projects. For example, University Technology Brunei, and Chinese Academy of Sciences, and Georgia University, and the university in Japan, in South Korea. So those collaborations allow us to exchange expertise, scale research, and apply our innovations to real-world challenges. Um, and also, I'm looking forward to establish some new partnerships with the institutions, with your institutions, and hope to create some more innovative solutions in robotic AI. So those are the photos took. So so we built up a foundation that will, with this foundation, we've driving advancement in autonomous systems, robots, and lifelong learning across the global. So now I've shifted my focus to the technical detail of motion and path planning, a key area of research in robotics. So let's take a moment to bridge the gap between theory and application in robots. So we've dived deeper into the specifics of motion planning or methodologies, and how those theories are being applied to solve real-world challenges. So this will showcase how robots research is evolving to tackle the dynamic and complex environments. So motion planning is and path planning are at the heart of autonomous systems. So they answer the fundamental questions: where am I going, and how do I get there? So in this section, we'll discuss some key planning techniques, from traditional methods like artificial potential fields to some cutting-edge learning-based approaches. So nowadays, we see robots are increasingly popular among industries in manufacturing, transportations, healthcare, and so on. For example, they we've seen the growing popularities of robots in the industries such as logistics, where Amazon uses robots to manage the warehouse, which is like shown in the first photo, and in hospitals with surgical robotics, and in autonomous vehicles like Tesla's autopilot. So the first one is warehouse robots from Amazon, and the robots can carry parcels and classify them, put them in the correct shelves. So the next one is a surgical robot in the hospital. It can do some simple surgeries for the patients, and assist the doctor. And the third one is the system Tesla's autopilot. It can automatically drive the car to the chosen destination without in collision with other cars and pedestrians. So we can see that the robots operating here are using three-part architecture, which is sense, which is gathering data from their surrounding environment, and then plan, which is deciding how to move or act based on the data collected from the sensors. And then the last step is act, which is executing those decisions planned. So motion planning bridges sensing and acting, so make it critical to the robot's autonomy and efficiency. So here are some other examples of motion and path planning, such as autonomous mining and city navigation. So navigation is the art and science of determining a robot, especially a mobile robot's position, and guiding it to a specific destination. So it requires a person to know the vehicle's relative location or position compared to the other known locations. And to navigate effectively, so usually the robot needs three fundamental competencies. The first one is a map interpretation, and including the self-map building. And the second one is path planning. And the third one is self-localization. So I will come to those one by one in more details. So map interpretation denotes any one-to-one mapping of the world onto an internal representation. So this must be understood by a robot or by an autonomous navigating system, and so their own representation might not be readable, understandable by the human. So robots must interpret or even build their own maps of that environment. And the second one is path planning, so which is an extension of self-localization. So it requires the determination of the agent's current position and the position of the desired goal. So they need to determine the best route to the destination, which is planning a path. Um, and the third one is self-localization. So this is the ability of the agent to establish its own position within the frame of reference. So robots must know their position relative to the map and to their target. So altogether, those skills enable the robots or the autonomously navigating system purposefully act in a dynamic and complex environment. And so those are the foundational motion planning techniques. So autonomous navigation usually comes with a host of challenges. The first one is robots often operate with partial knowledge of their environment, relying on maps and sensor readings, and they must reach their goal efficiently and reliably, avoiding obstacles without damaging themselves or their surroundings. And the dynamic environment with moving obstacles makes it even more complex. So in this area, so we are working on balancing long-term planning and short-term obstacle avoidance. We're using a combination of global and local planning strategies. So I will explore a little more details later. So path and trajectory planning are two interconnected aspects of motion planning. So given the map and the global location, so path planning involves identifying a trajectory that will cause the robot to reach the goal location when executed. So path planning focuses on finding a sequence of configurations to navigate the robot from its start to its goal without considering time. So it's a strategic problem-solving competency, and the robot must decide what to do over the long term in order to achieve its goal. And trajectory planning is moving from point A to point B while avoiding collisions over time. So trajectory planning is a major area in robotics as it gives ways to autonomous vehicle. So trajectory planning adds the dimension of time, determining when the robot should reach specific points along the path while considering velocity, acceleration, and kinematics. So within the mobile robotics research communities, a great many approaches has been proposed for solving the navigation problem. So there are strong similarities between all of those approaches, even though they appear quite disparate. So the key difference between various navigation architectures is the manner in that they decompose the problem into smaller subunits. So together, those processes ensure robots can move safely, efficiently, and dynamically in the complex environment. So such as, for example, autonomous vehicles navigating in the city streets or drones flying through some crowded spaces. So here are some key features of motion planning. So the algorithms are usually evaluated based on their complexness, which means can the algorithm always find a solution if there is one exists, and optimality. So is this solution the best possible one in terms of criteria such as time or energy efficiency, and computational efficiency. So how quickly can the algorithm compute a solution, especially in some real-time applications, and also robustness. So how well does the algorithm perform in complex or dynamic environments? So those features will ensure motion planning algorithms are reliable and scalable across different applications. So So generally, the motion planning can be divided into two main categories. One is a global planner. So those create high-level passes, identifying the waypoints needed to reach the goal. And planner ensures feasibility and optimize for efficiency over the entire journey. And also we have local planner. Those acts to changes in immediate environments such as new obstacles or dynamically adjusting the robot's trajectory. So many advanced motion planners are now integrating both approaches to ensure adaptability and long-term success. So here's an example. So imagine you are driving from the campus to the railway station, for example. So you are using Google Map to find a route there, so which is global planning. So and on your way, you are avoiding collision with humans and other vehicles. So that is local planning. So the Google Map can always find the route in limited time, or if not, it can always tell you that it fails in limited time. This is called completeness. And you always prefer the route that costs the least time, for example. So that is the optimality. Just one of the examples for that. And so a motion planning task can be normally defined to obtain the collision-free path from the start to goal for a robot that moves in a static or dynamic environment that consists of different obstacles. So the goal are to find the path that collision-free trajectory. So robot should reach the goal location as fast as possible. So the problem of motion planning can be stated as a startup pose of the robot, a desired goal pose, and we need to know the geometric description of the robot, which means the robot must know or have an indication of where it is in the map. And also, we need to know the geometric description of the world, which is a global map is needed. So to further understand motion planning, let's define a few key concepts. So the first one is configuration space. So this refers to the set of all possible robot configurations. So each of the configurations specifies the position and orientation of the robot in this environment. For example, in a 2D space, a configuration might involve just x and y coordinates, while in the 3D space, we also consider orientation angles as well. So use the configuration space simplifies the planning process by mapping the robot's physical environment into a mathematical space. So in the state space, we also represent the obstacles in the robot's configuration space as well. So each obstacle maps to a region where the robot's configuration would lead to a collision. For example, in the 2D space, an obstacle might be just a physical rectangle. So in the 3D configuration space, it becomes a larger area, accounting for the robot's size and shape. So the next definition is the obstacle region. So the obstacle region in motion planning refers to the part of the robot's environment where movement is restricted due to the presence of obstacles. So those obstacles could be static, like the walls, the furniture, or equipment, or it could be dynamic, for example, moving vehicles, humans, or other robots. So we define like free space and obstacle space. So the free space means the set of all configurations where the robot can move freely without collision. So for example, as you can see from the slide, so from the Q, there's a curve from the QI to the QG, which is a set of configurations where the robot can move freely without collision. And the obstacle space is a set of configurations that would result in the robot intersecting with an obstacle. And so for the environment with moving obstacles, the obstacle region is time dependent, right? So the algorithm must predict and account for their motion, which adds more complexity. So the obstacle region is critical in path and motion planning algorithms because the robot's trajectory must avoid this region while navigating from the start to the goal. the prevailing algorithms like sampling-based planners, which I will come back later in the slides, for example, RRT or optimization-based method, explicitly account for the obstacle region to ensure safety and efficiency. So by accurately modeling the obstacle region, so motion planners can generate collision-free trajectories and adapt to complexity and in the cluttered environment. So those are the classifications of the motion planning method. So broadly speaking, so it can be classified into two categories, which is model-based and data-driven. So the model-based method, like for example, artificial potential field, sampling-based techniques, optimization-based techniques, grid-based techniques, and reaction-based techniques, and data-driven method, including deep learning, which enables end-to-end motion planning without explicit environment representation, and deep reinforcement learning focuses on sequential decision-making for navigation and manipulation, and unsupervised learning, which incorporates the uncertainty as noises to make planning more robust. So the first one is artificial potential field, or APF, is one of the earliest methods in motion planning. So the robot is treated as if it is moving through a field of forces. So the goal exert an attractive force, pulling the robot toward it, and obstacles exert repulsive forces, pushing the robot away from the collisions. So the robot moves along the negative gradient of the potential field, naturally avoiding obstacles while reaching its target. So that's the general principle behind the APF. So, however, the APF has some limitations. For example, it usually gets stuck in the local minimum, where the robot can't escape certain configurations, and also it has high computational costs, especially in cluttered or complex environments. However, it still remains as a useful concept for understanding basic motion planning principles. And the next one is grid-based technique. It divides the environment into a structured grid of cells, where each cell represents a specific position or configuration, and obstacles are marked as occupied, while free space are unoccupied. So path planning involves finding a series of connected cells from the start to the goal. So we have a free space, right? So we talk about free space. So free space consists of all grid cells that the robot can move through without colliding with obstacles. So those cells are marked as unoccupied, and the robot navigates through the free space to find a viable path. And the size of the free space directly depends on the resolution of the grid. Smaller cells provide more detailed paths, but increased computational complexity. And also we have target space. So the target space represents the specific grid cells where robot goals or destination lies. So it is typically one or more cells that the robot aims to reach during its path planning process. So the planning algorithms prioritize finding the most efficient path from the robot's starting position to the target space. And the algorithm searches for a path through the free space that connects the starting position to the target space while avoiding obstacles. So if a connection exists, the algorithm will identify it. So otherwise, it concludes that the target space is unreachable. And so here are some popular algorithms for grid-based techniques, including A-search, which is heuristic-based algorithm that balance exploration and efficiency by estimating the costs to reach the goal, and also some other methods I'm not mentioning in more details. The features of the grid-based techniques. So it has several notable features. So they guarantee completeness, as I mentioned earlier. So meaning that a solution will be found if there is one. And also their performance depends on the grid resolution, as I mentioned in the previous slide. So high resolution grids allow for more accurate paths, but would increase the computation time and efficiency. So they are well suited for structured environment, such as warehouse or roadworks, where the map is predictable, but for some uncertain and unknown environment, it's not as efficient. And so the grid-based techniques will usually struggle with dynamic environment or when handling high-dimensional configuration spaces. So in such kind of scenarios, they are less efficient for certain robot applications like manipulation. So the next bunch of the method is a sampling-based planning method. So they are powerful techniques for solving motion planning problems in high-dimensional or complex configuration spaces. So instead of explicitly representing the entire space, so those methods explore the space by sampling random configurations and connecting feasible ones to find a feasible path. So the key features include probabilistic completeness. So those methods are likely to find the solution if one exists, so given enough time. And also they are effective environment with complex obstacles or some narrow passages. I will come back to that later. And also in terms of computational efficiency, so by sampling selectively, so they avoid the computational cost of explicitly modeling the entire space. And so the popular sampling-based motion planning method includes probabilistic roadmaps, which is PRM, rapidly exploring random trees, RRT, and different variants like RRT Connect and PRM Star. So they I will first introduce PRM, right? And so which is the most widely used techniques in motion planning, especially in some of the industries. So PRM samples random points in the configuration space and connects them to form a path and identifies paths by linking the feasible nodes. So if the nodes if the link between the two nodes doesn't have any obstacles, then this link is useful. Otherwise, it will be abandoned. So PRM explores but do not construct the configuration space, and it applies easily to the high-dimensional space, and also is best suited for multi-query problems where the environment remains static. And it works well for high-dimensional spaces, but it usually struggles with narrow passages. So, for example, like the figure shown in this slide. So, in some kind of a narrow passage problems, it usually fails to find the solution. And RRT, which is aggressively exploring the configuration space by incrementally building a tree of feasible paths, and it is highly efficient and adaptable to dynamic environments. So it is excellent for single query dynamic environments due to its fast exploring, and some of the extensions like RT Connect and RT Star improve performance and optimize the generated paths. But it usually struggles with the metric sensitivity, and the convergence rate is usually unknown. It's not guaranteed. So while we discussed the sampling-based planners, which are widely used and probabilistically complete, meaning that they are likely to find a solution if there is one. So they don't always guarantee the optimality, as I mentioned. So their strength lies in their ability to handle complex, dynamic, and high-dimensional spaces where traditional methods are not. So the next bunch of method is optimization-based motion planning method. So, which is an approach where the goal is to minimize a specific cost function while adhering to constraints and limits, such as the robot's kinematic constraints, limits, and obstacle avoidance and smooth trajectories. So, for instance, so an autonomous robot's cost function might include collision cost, which is avoiding obstacles along the path, and trajectory smoothness cost, which is ensuring the robot's motion is efficient and natural. You don't want a robot to behave, in a very weird way. And the other cost is clutter behavior cost, which is accounting for environmental complexity, which is, for example, clutterness and dynamics of the environment. So this optimization based approach is highly customizable. So because the planner's behavior is determined by how the cost function are formulated. So however, it requires hand-coded cost functions, which can be time-consuming to design and to tune, to train for specific scenarios. And so the optimization-based motion planning method usually relies on mathematical models to evaluate and refine those motion trajectories. So the cost functions are often expressed as integers, where key variables include obstacle objectives. So they calculate the collision cost by evaluating how close the robot gets to the obstacle along its trajectory, as shown in the figure below. So they all the waypoints along the robotic arm, for example, and how close of those points to the obstacle. So those are considered the collision cost and to be evaluated in the optimization algorithm. And the other variable is gradients. So optimization usually relies on computing the gradients to adjust the trajectory towards a more optimal solution. So for example, so we minimize a function that represents the obstacle potential, balancing trajectory smoothness with avoiding collisions. So by iteratively optimizing the robot's trajectory, we generate paths that satisfy safety, efficiency, and dynamic feasibilities. And so those methods is widely used in robotics because its adaptability and effectiveness in dynamic environment. So for example, in some real world scenarios like industrial automation, so robots can perform precious pick and place tasks, and also for example, autonomous vehicles, the motion planning paths that balance the safety and travel time, and also in the medical robots applications to generate collision-free paths for the surgical tools. However, so there are still some challenges for optimization-based motion planning method. The first one is local optima. So the motion planners can get stuck in non-optimal solutions depending on their initial trajectory. So I will talk about how we address these challenges in a few minutes in the later slides. And the next challenge is real-time constraints. So computing optimized paths in real time remains computational intensive, which is it's very challenging to get end-to-end solution by using optimization-based method. And the other challenge is tuning the cost functions, as I mentioned earlier. So customizing cost functions for different tasks and environments is complex and often requires some expert knowledge in this area. So still, optimization-based methods still remain a cornerstone for creating smooth and efficient motion plans. As you can see in our later work, we also incorporate some of the optimization-based method in our work. And so next, I will explore a little bit on how learning-based techniques are transforming motion planning. So, for example, deep learning and deep reinforcement learning methods are most not relying on explicitly represent the environment, and they have strong adaptability on changing environment. So since models can be trained offline, so the running time for them could be saved a lot. Thus, they are good for reacting to dynamic changes in real time. Besides, they can also used as a global planning tool because neural networks can function as a universal approximator. And neural networks can also help them to be implemented in an end-to-end way. So this is attractive for engineers and scientists since it can save the cost on data pre-processing as well as a tuning process. So the deep reinforcement learning could also make sequential decisions that incorporating time as well. So for their limitations, so most deep learning methods can just do one-step prediction, so they need a global planner. And for reinforcement learning method, so sparse reward problem might appear in large maps, and reinforcement learning methods are very hard to train. So if in a large map, only several reward points can be given to guide the training of the model, then the model might be found very hard to converge. And also, the reward shaping is also very challenging. So for some unsupervised learning methods, so they are better at considering uncertainty and noises from sensors compared with other methods. However, those methods would require certain local planners for obstacle avoidance as well. So in the next section, I will shift the focus a little bit to the robotic arms and manipulators, which play a central role in industries and collaborative robotics. So the robotic manipulators are versatile, capable performing tasks ranging from assembly and welding and to medical applications. So I will explore briefly the concepts of kinematics, dynamics, control architectures, and the transition from simulation to real-world applications through sim-to-real techniques. And so those are the key understandings how robotic arms interact with their environment more efficiently and adaptively. So Industrial 5.0 emphasizes the collaboration between humans and robots, so going beyond automation to include resilience and sustainability. So unlike traditional robots that work in isolation, so Industrial 5.0 introduces the collaborative robots that work or we call it cobots that operate alongside the human operators. So those robots enhance the efficiencies while maintaining the safety, adapting to the human operator needs in real time. That enables smarter manufacturing processes and better resource utilization. So industrial robots in sectors like automotive manufacturing operating in a high throughput environment. So here's some pictures. And the traditional robots, as I mentioned, operated in isolated cages, performing tasks like welding and assembly at high speed. However, those systems requires extensive programming, leading to a significant downtime during reconfiguration. So the trend is with collaborative robotics, we are moving towards greater flexibility, allowing robots to operate closer to human operator while simplifying reprogramming through learning by demonstration, for example. I will come back to that point later. So those are designing options, solutions for the robotic arm, which involves several key components. The first one is identifying the objects to manipulate and their positions, and then configuring the ND effector and low-level controllers for precise handling, and then implementing trajectory planning and intelligent control architectures to achieve the desired motion. So sensors and virtual simulation environment are often integrated to ensure the robust design before deployment in the real world. And as you all know, that safety is paramount in robotic systems, especially when working alongside the human operators. So there are some standards such as ISO, TS, 15066 2016 outlines safety requirements for collaborative robots, which ensures human-robot interaction remains safe. So here are some links and some readings. And so those are some prevailing and popular collaborative robotics in industry. So the cobots are versatile and user-friendly, designed to work without physical barriers. So they operate at a lower speed, can be repositioned easily, and are often programmed via kinesthetic teaching, enabling a rapid deployment for some new tasks. I will come back to that later. It's how we can collaborate with the robot and how we interact with the robot. So the robotic arm and manipulators are mechanical systems designed to replicate human arm movement and perform tasks like lifting, assembling, or welding. So, but they vary in design, functionality, and number of degree of freedoms. So, which defines their range of motion. So here are some different types of robotic arms, like articulated arms, or which is most common design, resembling a human arm with multiple rotary joints, which has high flexibility, making them ideal for complex tasks like welding or assembly. And the other one is selective compliance assembly robotic arm, which is designed for tasks requiring high precision in a 2D plane, such as pick and play operations, and is compact and fast. And some other arms like Cartesian robots, so which are operating on 3 linear axes, X, Y, Z, moving in straight lines, ideal for tasks like 3D printing and CNC machining as well. And other arms like a cylindrical robots combined rotary and linear motions, working with cylindrical workspace, so used in some simple tasks like handling machine tools. And the spherical robots operating with spherical workspace with rotary and telescoping motions, so useful in arc welding and material handling as well. And the degree freedoms, so which means the number of independent movements a robot arm can perform corresponding to its joints. So here are some basic degree freedoms of the traditional and prevailing robotic arms, like 3-DOF, which is a basic linear or rotary motion often found in Cartesian or cylindrical robots, and 6-DOF matches the mobility of the human arm, enabling positioning and orientation in 3D space. And 7+ degree freedoms, so which adds redundancy, as we know that so the overall 3D space can be categorized as 6 degree freedom, and 3 degree freedom for the positioning, and 3D for the orientation. So 3+ degree freedoms add some redundancy, which improve the flexibility to avoid obstacles or operate in a constrained space. So the robot I'm going to talk about later in the slide, which is a Franca Panda robot, which is 7 degree freedom, which has 1 degree freedom redundancy. And so here's another very popular robotic arm, which is a universal robotic arm produced by Denmark company, which are lightweight, flexible, and collaborative, designed for a wide range of industrial applications. And so it's a cobot, collaborative design. And also it is very easy to program. It has an intuitive programming interface and flexibility, combine different models in varying payload like UR3, UR5, UR10, and can be used for tasks like assembly, packaging, welding, and more. And 6 degree freedom, it has 6 joints and offering high flexibility and a wide range of motion. So next, I'm going to talk about the end effector types. So the ND factor are very critical for robotic arms as they determine how robots interact with their environment. So the common types include parallel grippers, and which simple and widely used for pick and place tasks. And the other one is three finger grippers, as you can see in the second figure. So which provide dexterity for handling irregular objects, and also vacuum cups, which is ideal for smooth surface like glass or metal, and magnetic grippers, which is effective for handling ferrous materials. So more advanced in factors, like I mentioned, such like soft grippers and gecko-inspired grippers, for example, which enables robots to manipulate delicate and unconventional objects safely. So part of our work is also involved in the software robotics design and control system as well, but I'm not going to cover in this presentation. Perhaps in the future we can have more discussion and exchanging of ideas in that direction. So robot kinematics. I understand that there was another talk covered by another lecture and specifically on kinematics. So I will not go into details in this part. So just quickly skip it. So as you all know that kinematics is the foundation of the robotic motion, enabling us to determine the position and orientations of the robot in the factor based on the joint angles. So we usually need to handle with the forward kinematics, which calculates the position of the end effector based on the joint rotations, and inverse kinematics, which determines the required joint angle to achieve a desired end effector position. So both of these kinematics are critical for trajectory planning, which ensure the robot moves precisely and efficiently to complete the task. So here is an example of the robotic kinematics of the universal robotics. So including DH parameters, transformation metrics, and forward kinematics, and the output as well. So here's another example of robotic kinematics, joint and end factor for Panda, Panda arm, and also the universal robotic arm. So path planning defines the high-level route for a robotic arm, while trajectory planning focuses on the motion between the waypoints, considering velocity, acceleration, and smoothness. So it includes key steps such as the start and goal states, and the search algorithms, and path smoothing, and the execution of the path. So trajectory planning come into play once the path is determined. So it focuses on specifying the robot motion between the waypoints along the path. So considering factors like, as I mentioned, velocity, acceleration, and jerk. So the key steps would include defining the waypoints from the start to the goal, and also allocating time for each waypoint to ensure the smooth motion, and then calculating the velocity and acceleration profile for the precise control. And next is doing the inverse kinematics, feed forward and feedback control, and also collision avoidance method, and also real-time adaptation. So those processes enable the robots to navigate complex environments safely and efficiently, so adapting to real-time changes when necessary. And so both path planning and trajectory planning are essential for effective robot motion, as I mentioned. So path planning provides a high-level plan to reach the goal, while the trajectory planning refines that plan by specifying the detailed motion and control parameters to execute the plan accurately. So altogether, those processes enable a robotic arm to move safely and efficiently in a complex environment while achieving its objectives. So robotic manipulation involves controlling the end effector to interact with objects requiring precise movement and feedback. So, and the open loop control which means pre-programmed actions without feedback, and closed loop control, what we call it, it's real-time sensor data adjusts the movement dynamically. So, and we also consider visual serving or vision-based control, which is making use of machine learning and deep learning or reinforcement learning to enhance the robotic perception to allow robot to detect, grasp, and manipulate objects accurately, even in a dynamic setting. So here's an example of controlling robot arm using Move It. So control robot arm involves moving a robot arm to a position, gripping object moving to a location and releasing the object. So visual serving could also be used to detect objects as well as its location. So gripping an object, moving to a location, and release the objects. So here are some examples of controlling the robotic arm using kinematics and forward kinematics and inverse kinematics. So I'm running time, so I will skip of those slides. Robot arm poses. So we define grab poses and approach poses as well. So how we design the robotic arm solutions, we consider positions, indicators, low-level controllers, as I mentioned, and incorporating with sensors and control architectures. So those are simulators like Gazebo and Cooperlear Sim, and to respect the physics, providing realistic scenarios for testing. So now here are some key some recent advancement and some readings and now I'm so motion planning is in robotics become very more complex when robots must operate in a dynamic, cluttered, and uncertain environment. So to address those challenges, we've developed a long-term cognitive motion learning architecture, so which focus on continuous learning, multimodal sensing, and adaptive learning. So I will give you some bit of ideas. So here are the motion planning in complex environments could include the dynamic constraints and human-robot collaboration, some large space with constraints beyond sight, and some narrow space such as corridors. And so robots operating in dynamic environment face some challenges. For example, constantly changing obstacles in a dynamic environment. Some uncertainties caused by sensor noises or incomplete information, and some cluttered spaces as well. So to navigate those scenarios, the robots require real-time perception, so predictive modeling, and robust decision-making capabilities. So in order to do that, so we are conducting some kind of benchmarking works in motion planning and motion learning. So we consider time efficiency, how quickly a planner generates a solution, and we consider success rate, and which means the ability to achieve the task without conditions. And we also evaluate the parameter sensitivities, which means how robust to environmental or configuration changes. So we compare different prevailing motion planners using different planning scenarios and different planning tasks with physical robots in real-time kinetic feed. So those are the metrics across different robotic arms like Franca, UR5, and KUKA. So we evaluate spans multiple configurations like a single plane, a semi-closed box, and living room drawer. So different scenarios. So here are some listed single query planners we used in benchmarking, including some prevailing motion planners such as RT Connect, RT Star, and KPs, etc. So here is the first scenario. I will accelerate a little bit. So which is a relatively simpler pick and place task on the open desktop. And this is another benchmarking scenario, which is relatively challenging pick and place task in a restricted workspace, which is bin picking problem. And this is a benchmarking for the scenario 3, a more challenging pick and place task in restricted workspace combined bin picking. So we conducted environment configuration benchmarking and parameter sensitivity benchmarking across different scenarios, which include comprehensive analysis, scenario-based evaluation, and weighted average across scenarios. So our research evaluates planners by measuring their time efficiency across diverse scenarios, and then use a weighted average to rank the planners based on the overall performance. Yeah, so here are some results of the benchmarking. As mentioned earlier, so traditional optimization based on motion planning method usually suffer from the challenge of local trajectory optimization. So it often gets stuck in local optimal, depend on the quality of the initial solution. So often do not find a solid collision-free trajectory and often require a fine-tuning of the cost function. So we came up with a novel approach to teach the robot various feasible ways of doing a task and let the robot learn autonomously from a human expert. So in the process, so all the data from the robot are collected for training, including velocity, position, and acceleration. So we propose a probabilistic movement primitive, which is a powerful framework for improving motion learning and motion planning. So it models the trajectories as Gaussian distributions, capturing the variance and optimal behaviors demonstrated by the human during the training. And so at every time step, we feed a Gaussian distribution over the state, and we use it to set a quadratic cost function, which captures a mean and covariance. So the result shows that our method generates trajectories that exactly reproduce the demonstrated distribution. So we also introduce another parameter to capture the mean and variance of the weight vector. And we applied conditioning by adding a desired observation to the probabilistic model. So the ND factor can also adapt to the new goals in task space. So for trajectory optimization, we define the trajectory smoothness cost and an obstacle avoidance cost, as I mentioned earlier, and we calculate the gradient. So this allows us to conduct collision-free and smooth trajectory optimization. So generally speaking, we generate motion trajectories using prompts from the human demonstrated trajectories, which is training data, and those trajectories are adapted to the new desired end factor configurations as well. So we sample the weight vector from the learned distribution and conduct motion trajectory optimization. So the key feature of our method include adapting to the new goals. So the robot can adjust the learned trajectory to fit a new environment or tasks, and it's collision-free optimization as well. So we optimize the trajectory using cost functions for smoothness and obstacle avoidance. So by leveraging prompts and learning from human expert demonstration, so we enable the robot to learn from the demonstration and generalize their behavior to the new scenarios, as you can see later in the video. So such as grasping objects in cluttered spaces. So we teach the robot, we demonstrate how the feasible trajectory can be, and then the robot will learn a new trajectory and generate and execute a trajectory. And when the environment changed, for example, like the table orientational table changed, so it is still able to adjust and adapt to the new orientation to the changing of the environment as well. So the next part of the work, I'm aware of time. I'm going to quickly go through them. So this is another work focusing on easily adaptable and learning, so which combines imitation and meta learning to create some highly adaptable systems for pick and place tasks. And so robots learn from previous demonstrations and enable some rapid adaptation to the new environment. And the meta-learning ensures the system can generalize even when the camera configuration or workspace layout change. So this work um, will significantly reduce the need for reprogramming, make the robot more efficient. So it is work still ongoing. And we also include multi-sensory feedback that enhance the robot performance by combining data from multiple sensors. As you can see from here, from multiple sensors from multiple configurations. And however, the reconfiguring the sensor setups pose some new challenges, which we address through meta-learning techniques to adapt quickly without any retraining. And so the next part of the work, which is also belonging to the architecture, which is addressing the robotic singularity problems. So the singularity problems occurs when the robotic arm motion becomes undefined due to the Jacobian matrix becomes in singular. So this leads to issues like erratic movement or unachievable configuration. So as can be seen from the slide, some traditional motion planners are effective for general motion planning, but they struggle near singularities due to the difficulties in handling the non-invertible Jacobian matrix. So we introduced a damping factor in the motion planning framework, so which helps stabilize the inversion or near singularity or EU conditioned Jacobian matrix. So controls the trade-off between the stability and accuracy. So we integrated with learning from human expert demonstration as well. So and the probabilistic movement primitives from recording demonstration using prompts, encoding the demonstration and reproduce the demonstrations. So our solution involves damped least square and prompts, so which stabilize the inversion of near singular matrix and handles singularity problems. So which means we introduce a damping factor which controls the trade-off between the stability and the accuracy, and also there's a pseudo-inverse Jacobian provide a least square solution to manage the underdetermined or overdetermined systems. And learning from human expert demonstrations will make the robot adapt to robot limitations and workspace constraints. So here is the overall overview of the framework, and so our work, the results shows that the DLSIK, which is the method we propose, greatly improve the robotic arm performance by maintaining the stable joint position and reduced abrupt velocity changes for smoother motion, and also contribute to manage the torque more efficiently to prevent some hardware damage. So here are some applications we have, including some human-robot collaboration, so enhance the safety and adaptability in shared workspaces, and also as you can see that some applications in the agricultural environment for perception and planning motion and doing the cutting work, harvesting. So generally, we're using different kind of vision sensors, which is, as you can see, the hand-eye system here, which is an inter-real size sensor. And we have a fixed sensor as well, which is a Kinect, fixed on frame. Okay, so I'm aware of time, so I will quickly go through the future trends in robotics AI. Because this area is evolving rapidly, so driven by emerging trends and technologies. So they are not just about making robots smarter, but also making them more adaptable, ethical, and impactful. So I will explore some of the key areas shaping the future in this area, in my opinion. So I saw some opportunities for collaboration and explorations. So the hot topics in this area. So some of the hot topics include AI in safety critical systems, which means we're incorporating AI into systems like autonomous vehicles and healthcare, where safety and reliability are paramount. And digital twins, some virtual replicas of physical system for real-time monitoring, predictive maintenance and optimization, and also automation and decision making. So the algorithms like that improve resource allocation, task scheduling, and system performance. And other hot topics like IoT integrations, real-time control and monitoring of IoT devices in some domains such as agriculture, aquaculture, and manufacturing, and predictive maintenance. So using AI to forecast system failures and optimize the maintenance schedules. And so the future of robotics AI research will be defined by advancement in some key areas. For example, like sustainable computing, which means to design energy efficient systems and integrate renewable energy resources, and also ubiquitous real-time computing, so reduce the latencies in computing and communication networks to enable seamless edge computing. And also collaborative autonomous systems. So robots working collaboratively in distributed network, sharing data and decision in real time. And the other areas, AI-driven distributed systems. So system can self-optimize and adapt dynamically to the environment changes. And so there are still some untapped opportunities in this area, for example, like bioinspired systems, to draw some inspirations from nature to design adaptive and resilient systems, and cognitive IoT to integrate AI with IoT devices for intelligent decision making and autonomous behavior. And AI, sorry, any
No, Professor, continue.
Sorry, I may need to exactly. So I'm running time, but I think there are a few slides left. Have you?
Yeah, please. You continue.
Okay, fine. Yeah. So the other one is the AI task characteristics. So we need to address the unique challenge of AI tasks in real-time systems, such as managing dynamic priorities and resource constraints, and also some other areas in harsh and unpredictable environments. We need to develop systems that can operate reliably in some extreme conditions, like in the space, in the underwater, or in some disaster zones for rescue, for example. And obviously, collaboration is key to advance the robotics and AI in this area. So here are some of the most promising areas, in my opinion, for collaborative research. The first one is sustainable and green computing. So to design some energy efficient systems and eco-friendly IoT devices, and quantum computing in distributed network, and AI and machine learning for safety critical systems, and also bioinspired robotics, and also obviously cybersecurity for autonomous systems. So at the end, in the last part of my presentation, I invite the aspiring researchers to join us in exploring bioinspired models, soft robotics, and cognitive motion planning and motion learning. So there are opportunities for example, pursuing a PhD at York, and for academic visits, for staff, student exchange, or even for some joint student supervision, etc. So our projects are focusing on real-world challenges. So we have loads of opportunities to contribute to the groundbreaking advancement in this area. So if you are interested in any of those areas, please get in touch with me. And lastly, I would encourage all of you to contribute to the special issue I'm currently organizing, which is a second edition this year. Attracted a lot of attentions in the first edition, so we are invited to put forward a second edition. So this is on the journal Biomimetics, which is a Q1 journal with an impact factor of 4.5. So the aim is to highlight the roles of advanced bio-inspired and biomimetic intelligence for robotics applications and some prior knowledges in achieving some success, and how they contribute to the taming of the complexity of some linked domains. Like I believe mechanical engineering and mechatronics are one of two of them as well. So the topics are not limited as listed on the slides. And I'm also organizing the 26th towards Autonomous Robotic System TAROS conference, which will be held at the University of York in August 2025. It's a long-standing historical robotic and AI conference in the UK, which is very a popular conference as well. So the key date is 21st February. It's a deadline for abstracts, and 28th of February is a deadline for paper submission. And here's another international conference I'm organizing this year. So the fourth international conference on artificial intelligence and autonomous robot systems, which will be held in Bristol. So the submission deadline is March 23rd, 2025. Okay, so thank you for your attention. I'm worried that I'm slightly over time, so I look forward to your question and discussion how we can advance this area, and I'm looking forward to receive any interest you may have for further collaborations. Thank you.
Yeah, thank you, Professor. It's a wonderful session. I think all participants they are happy. I think few participants they are going to ask questions. I think those who are interested to ask the questions, please switch on your camera and switch on your mic. I already gave the permission.
Yeah, I noticed there are some questions in the chat, but I couldn't see it in the when I went to the presentation. I'm just looking at those questions in the chat.
Professor, in chat, they are mainly focusing on attendance and feedback. They are looking.
Okay, that's fine. I mean, if any attendees have any questions, just unmute and feel free to
yeah, please unmute your mic and unmute your camera.
Hello, sir. Sir, good evening. I'm Mohammad Shahid Khan. We have interacted earlier also. Sir, as you mentioned, the journal Biomimetics.
Yes.
So is it SCI index also, sir?
Sorry, can you say that again?
The connection what he is asking, the journal you are going to, the special issue, it is a SCI indexed, Science Citation Indexed.
So it's indexed by ICI. So it has the impact factor of 4.5.
Yeah, the second thing is that is there any charges, publication charges?
Yeah, so yeah, there are some article processing charges. Yeah.
Okay.
Yeah. So if anyone is more detailed, I can share a link.
Yeah. Sir, I've already prepared few research articles which can be submitted in your conference. So you are actually going to organize 2 to 3 conferences, I think, as you mentioned just now. So yeah, so is it fully sponsored, or we need to sponsor ourselves?
I'm not sure whether I quite understand your question because of the
Professor, what he is telling, he is going to submit a paper on your conference. You are going to organize 2 conferences. Out of any one conference, he is going to submit a paper.
Oh, that's great.
I think you remember this Mohammad Shahid Khan. He is my student, I think, Professor.
Oh, okay, great. Okay, yeah. Okay, great. Yeah. So if you would like to send I mean, when you have a draft or abstract, if you would like to send to my personal email, that would be great. I can have a look before submit. Yeah. But yeah, welcome.
Okay. Yeah, other participants, do you have any questions? I think it's already late. Please, if you have any questions, please respond. Yeah,
Sir, thank you. Explain. Hello.
Yeah, please.
Yes, sir, sir, can you explain the application of forward and inverse kinematics of robotic manipulator?
So
Real time application actually, where we just now it is being used.
yeah, so we use yeah, so we usually use it for so it's automatically calculated. So we are using, for example, using Move It. Do you know Move It?
Yes, yes.
So yeah, it's a ROS tool. So it is automatically calculated. There is a solver in the Move It library, so it's automatically calculated when we are doing some motion planning tasks. Yeah.
Hello,
Thank
sir.
you.
Yeah, yes, please.
Sir, I am Dr. Kiran from Geetam University.
Yeah.
Okay.
So I was working with Turtlebot in ROS for autonomous navigation.
Okay.
So I'm having one doubt, like how can we generate the grid-based map in real time is one question. Yes, and also I want you like, can you provide any resources that I can go through it to do this kind of projects?
So can you say it again? So can
Yeah,
general
Professor is
what kind of
asking,
map?
he is working on Turtle robot. How you can generate the real-time mapping
And
for autonomous navigation, I think.
yeah, I was
Okay.
like a SLAM-based autonomous navigation I have performed.
Okay.
But how can we generate the grid-based map in real time?
Okay. So we are, for example, because we are using Panda robots for time being, and we use different kind of vision sensors to help us to generate real-time 3D point cloud, for example. And then we turn those 3D point cloud into bounding boxes, and we obviously we segment the scenarios we percept, and then um, we distinguish them into objects and obstacles and target, and then we do the motion planning. So then the bounding boxes will be turned into an octimap. So which means it represents how the space is occupied by the obstacles.
Okay, so
Yeah,
can you provide any resources for going through these kind of projects?
I think this principle is quite fundamental. So if you go to, I mean, if you mentioned that you are using ROS, right? So if you go to the Move It tutorial, so there are some information
No,
over
sir.
there. And
Move it for manipulator, but I'm using mobile robot.
okay,
So to autonomous navigation, so I use SLAM based mapping.
okay, I understand.
Instead
I
of that,
understand.
if I want to use another mapping,
Yeah, so I believe there are some open sources on GitHub to to explore for real time SLAM. Yeah, but I'm not working in the SLAM area. So currently my pure focus is on the manipulation play with robotic arms. But I believe because the official robots for ROS is a total robot, so it has some well maintained resources for total robots to for example to test your SLAM and etc. navigation algorithms. So I believe there are a lot of resources on GitHub or GitLab, so you can have a look.
yes. And one more thing, sir, I'm also trying the deep reinforcement learning.
Okay.
So can you just briefly explain how to create the virtual environment in doing this?
So for that, I think you can. So which simulator you are using for?
Same ROS only, Gazebo and Orvis. I am trying in simulation, and also I am facing difficulty in converting to real Turtlebot, converting that deep reinforcement learning.
Okay, so we we used another simulator, which is called OpenReef. I'm not sure where you heard about that or not. So it is a relatively less popular than Gazebo, but for the deep deep reinforcement learning purposes, we use that tools to do a lot of testings as well. I'm not sure whether but in one of the video in my presentation, so there is an environment that is showing that the open rig.
Can you repeat, sir? I'm not able to get it, the software or simulator.
I think it's open. It's open source, so you can. It's OpenRave, OPEN RAVE, I believe. So you can search and
Professor, if you don't have any problem, can you
Excuse me, sir.
write in
I have
chat
one
box?
question. Just
Write in
give
chat
me
box,
one
Professor.
time.
Professor, can you
Yeah,
write in
sir.
chat box? That's a simulation software.
Okay. Yeah. Let me.
Yeah, please type in chat box. They can understand.
Yeah. Okay. Let me give me a second.
Later, please write that one. I have some question with you. Actually, everything we are doing in India, in a simulator based, using ROS, means they have some drawback. Means whatever appropriate result we would like to explore, it's not possible. So, in your university, will you provide some hands-on if we apply for your PhD program? So, means such type of lab you have, will you provide during PhD? Actually, I already have PhD. I will apply. I would like to go for another PhD program. I got a better resource. Is it possible?
Uh, sorry. Can you yeah.
Huh.
Sorry.
Okay,
Professor, he is planning to
one more
apply
time I'm
under.
going to repeat. The thing is that whatever in India we are doing, also totally it's a simulator based. We are not doing means a real in a scenario to make some robot. Okay, actual
Okay.
robot.
Mhm.
So such type of facility in university in a PhD program,
Yeah.
you have such type of lab because in a Penville, I applied over there. They are for miss on campus student. They are providing such facility. MS student or PhD.
Yeah, so we do have a lot of facilities. For example, in my lab, I have different kind of robots for the student and for the academic visit researchers to play with and to doing piece of research. So are you seeking any sort of collaborations or um,
Yeah, Professor, I think your voice is not audible. Yeah. Hello.
hello?
Yeah,
Can you hear
Professor.
me?
Yeah, now it is audible. Now it is audible.
Okay. Yeah. I mean, if there are some potential collaborations or ideas you want to
That's good.
exchange, just feel free to email me, and we can organize another chat at another time. It's no problem. I'm very willing to collaborate with the researchers from your side.
Okay. Okay. Thank you, Professor. It's already late. I think you took more than 1.5 hour session. Yeah. First of all, I would like thanks to Professor Penching Liu for accepting our request and the nice lecture today he has given. I think I hope all the participants they have felt very happy. Thank you.
Okay, thank you so much for inviting me. It's a great pleasure to be here for having
Yeah,
this
Professor.
opportunity.
Thank you. Good night. Good night. Thank you.
Okay, good night. Thank you. Bye.
Bye. Bye. Yeah, I'm requesting all the participants, please fill the Google form for attendance and feedback. Both it is there in one form itself only. Okay, and it may close. The Google form link may close at 9:30 p.m. Please fill it. Okay, thank you. Again, we will meet tomorrow at 6 p.m. and I will share the tomorrow's link before 1 hour. I will share.
So what about day two, sir?
Day two, actually, I shared in Google Meet, but sorry, I shared in Microsoft Teams chat, but maybe you are not there, maybe, I think. Okay.
No, sir. That time maybe I might have
No,
moved
no.
from the system.
See, if you are really attending the program, you should be there at 6 p.m. to up to 9 p.m. Okay. And some people, they are just switch oning the camera, just and they are going here and there. It is not the correct way. Actually, we have shared, I already
Attendance
informed.
link, please.
Yeah, we already locked that day two attendance. Okay, we are unable to open again. Okay, thank you. Thanks.
Sure, sir. We'll take care. Yeah.
Sir, what about the regard recording sessions, sir?
I'm audible to you? Sir, sorry to interrupt you.
Yeah, all the recording sessions,
Sir?
I actually am trying to upload the YouTube and I will share the link and once it is completed, the validating session. Okay. In the
Sir,
WhatsApp group, in email also I will share. Don't worry. Yeah, please.
There is a one request,
Yeah,
Mr.
please.
Professor Praveen Bhojne. Actually, sir, kindly just request to the Professor Penching just to share the PPT, this session PPT.
Who
So that was wonderful.
Angshin Kim yesterday's.
Yeah.
Yeah, I actually
No,
I
this today's session, sir.
yeah,
This today's session,
I
sir.
requested every resource person, but actually some people they said they can't share. They are telling like that. But anyway, we have the video recording, and I can share. I can share that video recording to you.
Yeah, sir.
excuse me, sir.
Very-
Excuse me, sir.
Yeah, madam, please.
Yeah, sir. I'm Dr. Monica from the IIT Bhopal University, sir. Sir, I have attended